We'll record it for them. The second one here looks exactly the same, except it's not defined at that point. Is this one a continuous function? This is still a discontinuity, but it's a continuous function. So this was a no. This was a yes. Because it's not defined for this point down here. To be able to call it not a continuous function, you have to be able to point to you have to be able to see a point. There's a point there that is in, part of the function, but it's not continuous there. Every point that this function is defined is continuous, right up to each side there, even though there's a jump from one piece to the other there. There's not a point that you can say this kind of a statement. For any point that's on the function, the limit as you approach that value is the same as the actual function value. So this is a yes here. The limit, and pick any point here, even if you pick x equals 1.00001, right? The limit as you get close to that point is the same as the function value. What about this one here? Well, I guess with this break it's hard, but this, it's continuous at every single point here. These end values, it's continuous there because the limit, you can only talk about the one-sided limit, but it is, the limit as you approach from the left is the same as a function value. That's a continuous function. This is a continuous function. What about this one? Is that a continuous function? It is, right? It's got a hole in the graph there, but every point that's on the function, it's continuous. What about this one? This one's no, right? Because of that. The fact that it jumps there, that makes it not a continuous function. That's just a definition thing. It's not. It's hard to come up with functions like this just by plugging in one equation. You have to either make them piecewise functions or something like that. Any kind of polynomial function is going to be continuous. Any kind of rational function is going to be continuous. If you combine two continuous functions like that, we started talking about this last time. If you take two continuous functions and combine them together by adding, subtracting, multiplying, dividing, or constant multiple, as in I told you last time, if you take x squared, you know it's continuous, you know that's continuous. Adding them, they have to be continuous, and so on. We don't want to go back through that, though. What? If one's not continuous, then you can't argue that the combination is continuous. If you know, this is only saying if you know that these are both continuous, like then you don't know. Maybe it's continuous, maybe it's not, right? But this is saying if you know this, then this has to be true. The last thing is this intermediate value theorem here. It has to do with continuity. The intermediate value theorem is, it's going to be something that's kind of geometrically obvious when you look at the picture. Okay, let's suppose we have a function f of x, because we're really boring and we always call it f of x. You can change it to whatever you like. And let's say you have a couple values here, a and b, just a couple x values. If the function starts there and ends here, what are these values called? These y values. This first one's called, at a, it's called f of a in my case. And then this upper value here is called f at b, right? The function value at b. What this intermediate value theorem says is, if it's continuous, if the function is continuous on the interval a to b, if it's continuous on that interval, it has to hit every one of these y values in here. So if this is, if you draw it, it's kind of geometrically obvious. Whatever happens to this function, if it's continuous on this interval, from there to there, it has to take every one of those values, right? If it's continuous means it's, every value is what you expect it to be. There's not going to be a jump, right? If you did it where it's not continuous on that and it went from there up to here, then it's going to skip some of these y values, right? It's going to cover these ones and cover these ones up here, but it's going to skip the ones in the middle. If it's continuous, it has to hit every one of those y values. if you start on the second floor of a building in the elevator and you go up to the 12th floor, if you're traveling continuously along, time, however long it takes, right? If you have a graph of time and height here, if you know that it's continuous ride the whole way, you got to hit every single height at some point. Every height between the second floor and the 12th floor. Okay? I've got this thing to show you here. Hopefully this is going to help. Except I put it in the wrong place. Put it over here. Come on. There we go. It is opening. Okay, so this, on an interval here from whatever you want, from -2 to somewhere over here, 1 or something like that. If I start at, let's do this. That's definitely, I meant to do this one. So we're going to start at -2 here, right? Actually, let's start at -3. So let's say on an interval from -3 to 1. On that interval, is this function continuous? It is not, right? There's a definite jump there. If the thing is not is it a continuous function, but is it continuous on that interval? No. Okay, it's not continuous on that interval, so there's nothing that says it has to hit this red line doesn't have to hit every y value as I go to the right here, right? It's taking on every y value from here to here, because it's continuous on that interval. It's continuous on this interval, so it has to hit every single height from -2, right, from this value up to this value. It has to hit all those heights. But then, since there's a discontinuity there, it jumps from one to the other. Again, when you think about it, it's sort of obvious looking at the picture, right? If there's a break in it, it's not going to hit all the heights there. And it keeps going, right? If this wasn't filled in here, like I think if you mean this, let me try this here. No, that's the wrong one. Which one is that? That's this. Sorry. I'll make this one white. There we go. Like that? Yeah. So if that's like that, the thing is now we've got a function that's continuous, but it's still, if you talk about an interval, this is a continuous function, but on the interval -3 to 1, it's not continuous on that interval. It's saying something different to say, is it continuous on this interval, or is it a continuous function? It's a continuous function because for every single point, it's continuous, except if you talk about this interval, from 3 to 1, it's not continuous because it has a discontinuity there. So we're talking about continuity on an interval here. Right? If you go from there to there, it misses those things. If we change it and slide this down here, right? That's continuous now. Now, as you go up here, it has to hit every single height from the lower value to the upper value. At some point, that red line was at every single height from -2 up to whatever this 4 here, or no, whatever the value is at 1, that value. On that interval, -3 to 1 or -3 to 2, it has to hit every single height now. What? If I put this over here, it's only a one-way relationship here. If it's not continuous, it still might take every value. Like this is going to take on every value just because of the way it is. Like at some point, it's at every height between -2 and up here, wherever. But you can't guarantee it because there's that break. What you can say is if it's continuous, if the function's continuous on the interval, it has to hit every single value there. Okay, so can we try and write this out in a somewhat formal... Why did that skip all the way there? Okay, so again, what we're saying here is if the value, or if the function you're looking at, if f of x is continuous on the interval AB, got to get it in before my 10 minutes are up, then f of x takes, oops, can't spell. Panic. I have a buffer zone here. How if we pause it?